Hi everyone. So I want to start this week before we move on to looking at the last part of molecular orbitals by just clarifying and going over that final question from the revision questions last week. Basically the question asked you to draw how the orbitals overlap in a molecule of ethane, but that should have read ethene rather than ethane. So I've marked your answers based on ethene and not ethane. So I'm just going to quickly go over it just now. So we have our carbon atoms. Each carbon atom shows sp2 hybridization, which means it has 3 hybrid orbitals here. And we have 2 carbons displaying that. These 2 sp2 hybrid orbitals overlap, and that is our sigma bond between the carbon and the other carbon. We then have our hydrogen forming a sigma bond with the other 2 sp2 hybrids on the carbons. Okay, but remember, when we show sp2 hybridization, we still have unhybridized p orbitals, and they sit with their traditional p orbital shape, that dumbbell shape. They sit like that with respect to those other carbon atoms. So we've got a end-on overlap forming all these sigma bonds, and there's 1, 2, 3, 4, 5 sigma bonds in ethane, and then you have these p orbitals showing a sideways overlap along that way, forming the pi bonds. So we're just going to continue from where we left off last week, and in the questions that you completed last week, we started to introduce alkynes. There was a couple of questions based on how many pi bonds you might find in an alkyne and what type of hybridization you might see, but we hadn't actually looked at that at this point, but it was just interesting to see what sort of answers you were putting for that. So unsurprisingly, a lot of you were getting this right. An alkyne contains 2 pi bonds. An alkyne contains this carbon-to-carbon triple bond. So if a double bond contains 1 sigma and 1 pi, it would make sense that a triple bond contains 1 sigma and 2 pi bonds, and that is indeed what happens. It displays sp hybridization. We form these sp orbitals made up of 1 s orbital and 1 p orbital, and it leaves us 2 unhybridized p orbitals, which then go on to form the 2 pi bonds that are displayed in the triple bonds. These structures become quite complicated to draw, but I'll try and highlight that best I can on the next slide. So here we have some diagrams showing you the arrangement of the orbitals in an alkyne. These yellow orbitals here represent the hybridized sp orbitals, and you can see that they lie in a nice linear shape. We have a hydrogen here and a hydrogen here, forming a sigma bond with sp hybridized. So we've got a sigma bond there, a sigma bond here, and a sigma bond there. The p orbitals lie perpendicular to the sigma bond, to the hybridized orbitals, and we have 1 p orbital shown in red and 1 p orbital shown in blue, and you see that on both carbon atoms. These lie sideways, and a sideways overlap happens. That's shown quite nicely in this second diagram here. So the red p orbitals overlapping to form 1 pi bond, and the blue p orbitals overlapping side on to form the second pi bond. So let's pause for a second and think of what we have learned last week and then at the start of this week. We've looked at 3 different types of hybridization: sp3 in alkanes, sp2 in alkenes, and sp in alkynes. We've looked at how s and p orbitals combine to form a hybrid orbital. We're now going to take the idea of hybrid orbitals further and look at them out with the idea of alkanes, alkenes and alkynes, and we're going to look at a new class of compounds called aromatics. Aromatics we used to touch on them in the old higher course, but we tend not to do that anymore. But you may have heard of benzene. It may have cropped up when you were in higher last year. So the word aromatic was originally applied to hydrocarbons, so compounds containing carbon and hydrogen, which had a kind of sweet odour, a sweet aroma. But that has, as we've learned more about them, evolved more into a whole class of compounds that may not necessarily have that aroma, but all display very similar chemical properties and can undergo similar chemical reactions. Aromatic compounds are also known as arenes. So you might see that written in places, so just so you know what that means. And the most simple of the aromatics is this compound benzene. Benzene is a really interesting compound. We can do lots with it, and it's got displays really interesting bonding that we're going to look at on the next slide. So benzene has what we call an aromatic structure. And an aromatic structure is basically a ring structure, just like it's shown here on the left-hand side. And along with that, we have a set of delocalized electrons. The formula for benzene is C6H6, and that is because of these delocalized electrons, which we'll look at in a wee minute. Just to note that while benzene and compounds that have this ring structure and delocalized electrons we class as aromatic, any hydrocarbon that's not aromatic is aliphatic. Okay, so if I draw at the side here, this structure here, that's just the skeletal diagram for cyclohexane. Okay, because I haven't got that circle in the middle like I do in benzene, I would expect that coming out of each of those little corners, which we know is a carbon atom, I would have two hydrogens. Okay, so that's cyclohexane, that is aliphatic, and benzene with this circle in the middle representing the delocalized electrons is aromatic. So in terms of representing benzene and how you would draw it or draw its structure, there's a lot of debate over what is the most accurate way to represent it. So if we look at this first diagram here, we have our 6 carbon atoms in the ring with 1 hydrogen. These are all sigma bonds, these carbon to hydrogen bonds. And then we have alternating double bond, single bond, double bond, single bond, double bond, single bond. Now, we could take that a bit further and draw it as a resonance structure, which shows those double bonds kind of change in position. But the thing that makes this an aromatic compound is that these electrons are delocalized. These electrons are not necessarily always between these 2 carbon atoms or these 2 carbon atoms. They're delocalized into the center of the ring structure, which is why this is deemed, this one here with the circle in the middle is deemed to be the most accurate way of representing a benzene ring. But just to be aware, if you're looking at different websites, different textbooks, you will probably see it drawn like this in some places. So benzene shows a lot of different properties, and we can do a lot with benzene, and it's got great uses in the synthesis of different pharmaceuticals and all sorts of things. Usually when we're using benzene in a synthesis, we begin by forming this phenyl ring, and phenyl is just this C6H5 compound that is formed when you remove a hydrogen. This R group would just represent the rest of a molecule. An example of a compound that we base on a phenyl ring is aspirin, which is here. So here is our benzene ring, and up here we have a carboxylic acid group. Here we have an ester group. So we start with the benzene and we work forward from there, substituting at different points on the benzene ring with an R group. So benzene is the simplest of the aromatics. It can take part in lots of different reactions, but it is a pretty stable molecule. We have our 6 carbon atoms in our ring structure here. Each carbon in the ring structure is held together by a sigma bond. So we know that sigma bonds are really strong bonds, they're really stable bonds. They're much harder to break than pi bonds. So we have these 6 sigma bonds holding the 6 carbon atoms together. We also have, I'll just draw one to show you, sigma bonds here holding the carbon and holding the hydrogen to the carbon. But then we have an electron from each carbon atom that comes into the middle. So we have 6 electrons in the middle of this ring structure, and that delocalization, just like it does, for example, in metallic bonding, makes that really stable. So looking at those hybrids in a wee bit more detail now, each carbon atom in the benzene ring shows sp2 hybridization. So we have 3 sp2 hybrid orbitals. Each carbon atom will form 2 sigma bonds through those hybridized orbitals to another carbon atom and then 1 to a hydrogen. But that does leave us 1 unhybridized p orbital, and that will happen 6 times, and we'll look at that on the next slide. Okay, so here we are. This is quite a crowded diagram, but it does become quite crowded. It is a much more complex structure. So if you look here, we have our sigma bonds between each carbon to carbon. Okay, so we have 6 sigma bonds in the ring. We then have our sigma bonds to each hydrogen from a carbon. So that is taking care of our 3 sp2 hybrid orbitals. And then we have these unhybridized p orbitals. It's really hard to look at this without a model. And if we were in class, we would get a model. So remind me to show you that when we're back in school. The p orbitals have a lobe above the plane of the ring and below the plane of the ring. Okay, and I've got a few diagrams to help explain this a wee bit further to you. But if you can imagine, everything that is in that lilac-y colour is on one plane, it's all flat. You could put that whole bit flat against the table. And then we have 6 lobes above the ring from each carbon and then 6 below the ring from each carbon. So let's look at these diagrams, and I'll try to help you think in 3D as much as I can. This first diagram here showing you the sigma bonds, which we've spoken about in quite a bit of detail already. This second one, so this is all the sigma bonds here. This second one shows you the p orbitals, and you can see how we have 6 lobes above the ring and 6 below. Those p orbitals will overlap sideways to form a pi bond. Okay, so the electrons are all shared by carbon atoms. They are delocalized. Just keep in mind that they are delocalized within the ring structure. So they're delocalized within the ring structure. I've got another diagram to show you on this as well. So here's just another way of representing it. There is our ring structure in the middle there with our pi bonds at the top, pi bonds at the bottom. These pi bonds are what gives the extra stability to this structure. So while the pi bonds themselves are weak bonds, they do provide an extra stability to the benzene structure. But because they are weak, when it comes to chemical reactions, these are the first things that will be attacked. And we'll start to look at this when we start the synthesis topic. So let's have a little think, as we do now and then throughout this course, think about colours. We've looked at the colours of transition metals, we've thought about the colours of light and how they arise. I want to spend a little bit of time for the rest of this week's work to think about the colours of organic compounds, and unsurprisingly, molecular orbital theory can be used to explain why some organic molecules show a colour and some are colourless. Remember, most organic compounds are colourless. We see them as white, but have a little think. Think back to what we have looked at when it comes to colour so far. What causes colour? It's probably something to do with electrons and then some sort of energy gap. So when we started looking at molecular orbitals, we started thinking about atomic orbitals and how they combine when electrons are shared. So we also learned that when you form a bonding orbital, we also form an anti-bonding orbital, because we need an equal and opposite action to the formation of these bonding orbitals. But the anti-bonding orbitals don't just do nothing. We can promote an electron up into an anti-bonding orbital, and it is this promotion and subsequent falling back down of the electron which in some cases will cause a colour. So a couple of terms for you to learn here. We have our bonding orbitals. We might have sigma and pi. Electrons will fill these in order of increasing energy. And then we have our corresponding anti-bonding orbitals, so sigma star and pi star. The bonding orbital in which your last electron is placed is called the highest occupied molecular orbital, or HOMO for short. If we got to the anti-bonding orbitals, the first anti-bonding orbital that you come to, or the anti-bonding orbital that sits at the lowest energy, is called your lowest unoccupied molecular orbital, or LUMO. And in between your HOMO and your LUMO, there is a measurable energy gap. So there's probably a few bells going off in your head there. You're thinking about wavelengths, you should be thinking about absorption, emission, and complementary colours. I'm sure that's what you're all sitting there thinking. So the idea of colour when it comes to organic compounds is all related to this HOMO-LUMO gap, and the energy associated with that gap will obviously correspond to a wavelength. When electromagnetic radiation is absorbed, an electron will be promoted from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, which will be an anti-bonding orbital. Now, often that gap is quite large and requires quite a bit of energy, so the wavelength that is absorbed will usually fall out with the visible region in the electromagnetic spectrum, which is why most organic compounds you see are white. But sometimes the wavelength will fall within the visible region, and that means that a colour will be observed. So to understand why some organic compounds have a colour and others do not, we need to understand their structures. And we're going to start by looking at this idea of a conjugated system. And a conjugated system is actually quite simple. It's really simple to identify. It is just a carbon chain that has alternating single and double bonds. Okay, so if we have, let's just draw the skeletal structure of a carbon chain here. We have double bond, single bond, double bond, single bond, double, single, double, single, double, single, double, single, double, single. And that alternation, it gives rise to what we call a conjugated system. So each carbon in a conjugated system will have undergone sp2 hybridization, so will have formed 3 sigma bonds each, leaving an unhybridized p orbital to form the double bonds. Right, so when we have a larger system, like we have at the bottom there, this larger conjugated system, which we observe in a larger molecule, is where we tend to see colours produced. And the part of the molecule that is responsible for a colour being produced is called a chromophore. So it is responsible for the absorption of light in the visible region of the spectrum. So I'll start by just highlighting the homo-lumo gap. So less complex molecules, much smaller molecules than the one we see at the top here, have less occupied molecular orbitals. Okay, so less of these bonding orbitals will be occupied. So our highest occupied molecular orbital will sit lower down, and we would have fewer anti-bonding orbitals because of that. So our lowest unoccupied molecular orbital would sit a bit higher up. So that homo-lumo gap would be much bigger and would require something with a much higher energy that would sit outside the visible region of the spectrum in order to promote an electron. But when we have a larger molecule like this, we have many more occupied bonding orbitals. We would therefore have more anti-bonding orbitals, so that homo-lumo gap becomes much smaller, and therefore much less energy is required to actually promote an electron from the homo to the lumo. Okay, so here we have our, I'll just draw in the energy gap again. So we have our last electron in our highest occupied molecular orbital. And here we have our lowest unoccupied molecular orbital. And when we've got quite a small gap here, remember, because we've got many more bonding orbitals and anti-bonding orbitals. So that gap's quite small. So it takes much less energy to be absorbed in order to promote that electron up to the lumo. As that happens, we're absorbing a wavelength within the visible region, and we would observe the complementary colour. So I want to leave you today by looking at this question. So we've got 2 molecules here. One is orange and one is yellow. First thing I want you to do is identify the chromophore in each, and then try to determine which molecule is orange and which is yellow. So you can pause here, have a wee think about that, or just keep going and I'll explain it. So the first thing we want to do is identify the chromophore. So we have here the chromophore down here. So this is quite a big molecule. There is our chromophore in that top molecule. And here's our chromophore in the bottom molecule. Okay, so one of these molecules is yellow and one is orange. So if I write yellow and if I write orange. If you go to your data booklet and you look at this, it's page 20 of your data booklet, you'll see the complementary colour of yellow is violet, the complementary colour of orange is blue, and you also see their corresponding wavelengths. So let's write that in as well. So if you are seeing yellow, yellow will absorb, means that violet has been absorbed, and it absorbs at 400 to 450 nanometers. If we are observing orange, it means blue has been absorbed, and it's been absorbed at a wavelength of 450 to 480 nanometers. That information is just straight out page 20 of the data booklet. So if we think about our larger chromophore, a larger chromophore because there's more bonding orbitals, will have a smaller homo-lumo gap. It will require a smaller energy to promote an electron from HOMO to LUMO. And remember, a smaller energy refers to a longer wavelength. For our smaller chromophore, like the one we see at the bottom, because it's a smaller molecule, it's a shorter chromophore, shorter conjugated system, there will be less bonding orbitals and less anti-bonding orbitals. So there will be a larger homo-lumo gap. And if there's a larger homo-lumo gap, there'll be a larger amount of energy required to promote an electron from HOMO to LUMO, and therefore a shorter wavelength. So if we look at the values here that are being absorbed, the shorter wavelength is this one here. So we would expect this molecule to be yellow, and the longer wavelength, which is highlight them, the longer wavelength is associated with blue being absorbed. So we would expect to see this as orange. I'll leave you now to complete the revision questions for this week. Please just keep sending me emails, drop in sessions this week. Anything I can help you with, just get in touch. Good luck.